I think it's time to start. So it is my great pleasure to introduce Professor Thanh Son. So I think everybody knows him, but let me introduce about him. So he got PhD in 1995, Moscow, Russian Federation. So his advisor was Professor Rubakov. Yeah. And later he moved to US and University of Washington and several postdoctoral places, MIT and RIKEN and in BNL. So then he became an assistant professor in Columbia University from 1999, and he moved to some more places, University of Washington, and he became professor from 2007 at University of Washington, and finally, and later he moved to University of Chicago and as a university professor and several other institutes. I mean, Landau Fermi Institute, James Franck Institute. I mean, as many people know, first of all, I mean, he is well known to give a prescription for how to calculate transport coefficient in holography. So he got Dirac medal in 2018. According to the web page of Dirac medal, he was introduced in this way. Thanh Son was the first to understand that the basic gravity duality could be used to address basic questions in strongly interacting many-body systems, from cold trapped atoms to the quark-blown plasma. He was able to show that one could compute transport coefficients such as viscosity, conductivity, analytically in these systems. And particularly, he proposed viscosity and entropy bound, eta over S bound. So later, recently, he proposed another shocking some conjecture on condensed matter physics, particularly on fractional quantum mode effect and filling factor nu equal 1F. He proposed the so-called Dirac composite Fermi liquid theory, Dirac composite fermion theory, and this conjecture proposal promotes some fruitful discussions on dualities. And so, yeah. So today he will gonna talk about bosonization of Fermi. Is another some original and new topic and coadjoint orbits. So let's welcome Professor Thanh Son. Yeah, please. Yeah.
Hello. Thank you very much, Tisha, for your kind introduction. It is my great pleasure to give this talk at the APCTP Colloquium. Today I'm going to tell you about bosonization of Fermi liquids and how the mathematical method of Coadjoint orbits can be useful in physics. So the plan of my talk will be as follows. So first I will remind the audience about Landau's Fermi liquid theory. And then I'm going to point out that the Landau Fermi liquid theory can be understood as a dynamical theory of shapes of Fermi surface. And one can use the method of Coadjoint orbit to write down an action for this dynamics. We are going to talk about the group of canonical transformations and its Coadjoint orbits, which is going to be useful for our reformulation of Landau Fermi liquid theory. The work that I am going to tell you today is done in collaboration with Luca de la Cretas, who was a postdoc at in Chicago, and he's going to return to Chicago as a faculty member next fall. Isian Du and Umang Mehta are the two students in Chicago, and the paper was posted last March. Okay, so the beginning of condensed matter physics or solid state physics can be traced back to the work by Sommerfeld in 1928, where he corrected the previous model of metal called the Drude metal and introduced the Sommerfeld models of metals. According to Sommerfeld, the electrons in metal form a Fermi gas, and the quantum nature of this gas helped us to understand some properties of the electron gas that was very difficult to understand before. For example, the behavior of the electronic contribution to the specific heat of the gas of the solid from the electrons. And the Sommerfeld theory of metal also makes interesting predictions, like the Wiedemann-Franz law that govern the relative strength of conductivities with respect to electricity and with respect to heat. The ratio of the heat conductance and the conductivity is fixed by fundamental properties of fermions, quantum fermions, of the Fermi-Dirac distributions. So the Sommerfeld theory of metal was very successful, but there is a puzzle that was noticed right away, that in a metal, if you put in the numbers, we see that the typical value of the potential energy between the electrons is the same order of magnitude as the kinetic theory of the electrons. And so the picture that the electrons are free particles cannot be literally true. How can a theory that treats the electrons as free particles make so accurate prediction, while the electrons interaction cannot be neglected? This puzzle was solved by Landau in 1956 when he proposed a theory of Fermi liquids. Fermi liquid is the name that Landau gave to fermionic system with interactions. In Landau's theory of Fermi liquids, the an important concept was the concept of quasi-particle. And Landau showed that if the temperature of the fermionic system is low, one can show that the width of the particle, the quasi-particle, has a very small decay rate compared to its energy when we go closer to the Fermi surface. So the Landau Fermi liquid theory does not rely on the smallness of the coupling constant, but it relies only on the smallness of the energy scale or the temperature compared to the Fermi energy. And Fermi liquid theory has found confirmations and application in various systems in nature. For example, in helium-3 liquids, again in electrons in metal, neutrons in neutron stars should also form a Fermi liquid inside in the core of neutron stars, and many other systems. So Fermi liquid theory is the basis for our understanding of many states of matter, the Fermi liquid itself, and it also served as a base for other states like the state of superconductivity, where the fermion near the Fermi surface form a BCS pairing that leads to modifications of the Fermi liquid theory, the BCS superconductivity theory. More recently, some systems are believed to be non-Fermi liquids. Theoretically, one can construct the non-Fermi liquid by coupling the Fermi surface to a gauge field. Consider a fermionic system of finite density coupled to a U1 gauge field, or to a scalar fine-tuned to criticality, that is to mass equal to 0. And in that case, it is believed that the system becomes a non-Fermi liquid. Despite much effort, non-Fermi liquids are not very well understood. And one of the main reason is that usual tools of quantum field theory cannot be applied to the Fermi liquid, which is a very unusual state of matter, which has very many degrees of freedom. By the way, if there is any question during my talk, please interrupt me at any time. Let's return back to Landau's Fermi liquid theory. Landau's Fermi liquid theory is sometimes described in the literature, in textbooks, as a free theory, a theory where particles are free, non-interacting. And that is only
So question? Yes. In the previous speech, what do you mean the conventional usual technique does not apply to the description of non-Fermi liquid? So can you?
Yeah, I will mention it a little bit later, but basically the perturbation theory, for example, breaks down the infrared if one couple a Fermi surface to boson. So we don't have perturbation theory. Yeah, that's for one thing. I will mention other things later on.
I see. Thank you.
Sometimes Landau Fermi liquid theory is described as a free theory of Landau's quasi-particle, but the structure of Landau's theory is very different from free field theories in textbooks like pre-scalar field theory. So it is instructive to first describe the structure of Landau's Fermi liquid theory as originally sketched by Landau. Let's consider the first example, free fermions. Free fermions in Landau's method can be described by a phase-space distribution function, which is a function of time, space, and momentum. This is the number, the occupation number of fermions with momentum p at location x. And this function satisfies the Liouville's equation. The Liouville's equation describes how the distribution function evolved with time, and one can write it in the presence of any external electromagnetic field. So here you see the coefficient in front of the derivative with respect to x and respect to t in this equation is nothing but in the semi-classical values of x dot and p dot, where x is the coordinates of the particle and p is the momentum of the particle. So x dot is equal to the group velocity of the particles, and p dot is the Lorentz force acting on the particle. Now, one thing that one notice here in this equation is that as the Liouville's equation, it's conserved phase-space volume. And so if one starts the evolutions from an initial condition in which there is a sharp Fermi surface that separates a region in phase space with occupation number equal to 1 from occupation number equal to 0, then this initial condition is preserved at all later time. This kind of distribution function is similar to the distribution function in ground state at 0 temperature. Recall that in the ground state, the Fermi gas has a distribution function that jump from 1 to 0 at the Fermi energy. The Liouville's equation tells us that if we turn on an electromagnetic field, subject the system to any external field, the shape of the Fermi surface will evolve. But the fact that it's sharp, there is a region when f is equal to 1, separated from a region when f equal to 0, remain preserved. Landau's used these equations to extract physical properties of a Fermi liquid. In our case, just a Fermi gas at this moment. We can compute the linear response of the theory to an external, for example, scalar potential A0. So imagine that we turn on some A0 external potential, then that creates an electric field. Derivative of A0 is the electric field, which changes the evolution equation for F. One can linearize the previous equation and solve the Liouville equation to linear order in the deviation from the ground state from the unperturbed Fermi-Dirac distribution function. And after that, one can compute the response, that is the density created by the A0, and read out the value of the phi00 correlation function, density correlation function. And the result that one gets actually is the same, turn out to be the same as the result one would obtain, for example, by computing the one loop fermion graph in quantum field theory in the regime where the momentum of the momentum under consideration is small. And so the kinetic equations manage to capture the long wavelength correlation function in the quantum theory. Landau's contribution, one of the most non-trivial contribution, is to figure out the form of the kinetic equation when there is interaction between the original fermions. Landau proposed that the only thing that one needs to modify in the kinetic equation is the introduction of the so-called Landau parameter, which basically saying that the energy of the particle with momentum p is influenced by the distribution function at other momentum at the same place. So this very simple, just single modification lead to various interesting consequences. For example, one can predict the existence of a zero sound in many cases. The Fermi liquids support a sharp density fluctuation mode called the zero sound, which has been found. So the kinetic equation has a new term is subjected to a trivial modification. One needs to change the group velocity to the epsilon p over dp, where this is the total energy of the particle, including the influence from other, the presence of other quasi-particle, and also it influenced the change of the momentum of the quasi-particle. So this equation, if one knows the Landau's parameter, can also be used to compute correlation function. Now, let's return to one thing that we have mentioned before, that the Landau's theory can be thought of as the theory that governs the evolution of the shape of the Fermi surface. That statement is not violated when we introduce the Landau parameter in the formalism. It is because the fundamental equation is still the Liouville's equation, evolution in phase space, and the phase space volume is still preserved. And so the properties that the distribution function changes, the properties that the distribution function is only 1 or 0 is preserved under time evolution. So one can think about the Landau's Fermi liquid theory as a theory governing the time evolution of the shape of the Fermi surface. But one thing that one see from this previous discussion is that this Landau's original formulation of Landau Fermi liquid theory is very dissimilar to quantum field theory, classical field theory of quantum field theory. We have an equation of motion that doesn't follow from an action principle. And so we don't have access to a large toolbox of effective field theory. We don't have an insight from Wilsonian viewpoint on the Landau Fermi liquid. A field theory formulation of the Fermi liquid theory might be important for the problem of non-Fermi liquids that I have mentioned before. An example of a non-Fermi liquid again is 2 + 1 dimensional fermions at finite density coupled to a gauge field, and it's realized in fractional quantum Hall physics at half fielding. And without understanding effective field theory, without being able to think about non-Fermi liquid as an infrared fixed point of some renormalization group flow, one loses a lot of conceptual conceptual notions that would be useful to understand the properties of such a system. And so we would like to reformulate Landau's Fermi liquid theory as a field theory. And in this one transparency, I cannot give credit to all the previous attempts to write down such a theory. And let me only mention that there are two major directions. One is the direction that was pioneered by Benfatto, Galavotti, Shankar, Punchinsky, where one is trying to write down a theory directly in terms of the fermionic degrees of freedom, fermionic quasi-particle near the Fermi surface. And there is another set of approaches that is based on the idea of bosonization, that is trying to write the fermionic, the theory of Fermi liquid in terms of some bosonic degrees of freedom. That procedure of bosonization is very elegant in 1+1 dimension. But when we go to a higher dimension, 2+1, 3+1 dimension, this method becomes quite clumsy. And the specialists in this area would sometimes talk about technical details that are called patches or curvature of the Fermi surface that make the formalism quite difficult to use. So in this talk, I'm going to try to answer one simple question. That the question is the following: can one formulate Landau's Fermi liquid theory as a field theory with a well-defined action S is a functional of some field phi, so that delta S over delta phi equal to 0, the variational principle, give us exactly Landau's kinetic equation? The answer to this question is yes. And in order to figure out this action, one needs to use a method called the method of Coadjoint orbit. The result of this method is a higher dimensional version of bosonization, a higher dimensional generalization of the usual procedure of bosonization in 1+1 dimension, that is by construction a nonlinear theory. The main idea of the Coadjoint orbit method is the following. So if I take the Fermi surface of a fermionic system in the ground state, then it would have, the Fermi surface would have the shape of a disk, a round disk, assuming that the system is isotropic. If I now apply a canonical transformation, I will remind you what are the canonical transformations. The shape of the Fermi surface is going to change, and one can parameterize all the shapes as the result of applying canonical transformation to a given initial shape. So that's the main idea. The main idea is to parameterize the states of a Fermi surface as the result of a canonical transformation applying to the ground state. So let me give a very brief introduction to the notion of Coadjoint orbit, and then we will return to physics after maybe 2 or 3 transparencies. So let's recall some notion from the theory of Lie group, the algebra. So consider a Lie group, which I call G, capital G, and the elements of a Lie group can be thought of as an exponent, as a result of exponentiation of elements of the Lie algebra. So if capital F is the elements of the Lie algebra, then e to the f is the element of the Lie group. This also known that any Lie group has at least one linear representation. That is a joint representation that is defined on the Lie algebra. So basically the adjoint representation of the algebra is given by the commutator. So elements of the real algebra is mapped to another element which is equal to the commutator of what we want to represent, is G with F. And exponentiating this commutator, we get the adjoint representation of the Lie group. So here I am using somewhat of a loose notation that assume a unitary matrix representation, but the matrix U here would be the exponents of the matrix that give the adjoint representation of the algebra. Mathematicians define another representation that physicists usually don't think about. That is the coadjoint representation. For that, the mathematician defined the dual space. So the dual space, G star, is the space of all the operators that map elements of the Lie algebra to a number. So for any pairs of elements of the dual space in the Lie algebra, one can define scalar product. We can think about this way. This is if the Lie algebra is a vector with an upper index, then the dual space would be vector with a lower index. And by requiring that the adjoint representation does not change the scalar product, one can define the coadjoint representation that acts on the dual space. So if one acts on the two vector, one the vector in dual space small f and another vector in the Lie algebra capital F, by the adjoint and coadjoint representations of the group, then the scalar product does not change. That is the definition. That's how one can define the coadjoint representation. So for many simple groups, the coadjoint representation and the adjoint representations are basically the same. So for example, for simple this SUN group, they are the same, but for one can easily find examples where the coadjoint and adjoint representation are not the same. Now another notions that we need is the notion of the coadjoint orbit. And the notion is the following. So let us take one single vector in the dual space G star and apply to it all possible coadjoint acts on that. We act on that the elements of the group using the coadjoint representation. So we have a vector like F0, and then we act on that all possible elements in the group, and then we find a space, a subset space of the dual space called the coadjoint orbit. It's a set of all points in G star that is obtained from F0 by coadjoint group action. So now one can see that this coadjoint orbit is basically a coset G over H, where H is a subgroup that leaves this F0 invariant. Let's talk about a simple example of a SU2 group. So in the SU2 algebra is a three-dimensional space. An element of the algebra can be expanded in Pauli matrices, and we get a three-dimensional space. The dual space is also a three-dimensional space. And the scalar product between F and capital F is just a scalar product of these two vectors. Now, the adjoint and coadjoint representation in the SU2 group are basically isomorphic to each other. They are basically equivalent to SU3 rotation in the space, either of this capital F vector or small f vector. And the coadjoint orbit that is obtained from any non-zero vector F, F0, is just a three-dimensional sphere, because we acts on F0 element of SU2, it rotates F0 in three-dimensional space, and then give us a sphere. Any questions?
Question?
Yes.
Will you remind me what is H? You quotient G, quotient H. Yeah, what is H?
Okay, so here in this particular case, H would be all the elements of the SU2 group that leave F0 invariant. So these are the rotation around the direction of F0. So in this particular case, H would be SO2 or U1, right? And then the Coadjoint orbit is SO3 divided by SO2. So three-dimensional sphere, a two-dimensional sphere.
Okay, thank you.
General F0 define a subgroup that is all the elements of the group, original group that leave F0 invariant. That is called H. The Coadjoint orbit is the coset G over H. This example is a little bit trivial, but let's go to consider another group. That is the group of canonical transformations. Now the group is generated by the following infinitesimal canonical transformations, all of which are parameterized by a single function of x and p. So now x, consider a phase space of a single particle. The position of a particle in phase space is x and p, and in phase space we can define transformation x go to x prime equal this, and p go to p prime equal to this. So epsilon is something that is small, epsilon much smaller than 1. That is an infinitesimal transformation, and one can check that it preserves Poisson brackets. That is, the Poisson brackets of x prime p prime is still delta ij, and all the other Poisson brackets are 0. One way to see that is to think about f as the Hamiltonian. The transformation from x to x prime, p to p prime is a Hamiltonian evolution under a time epsilon, under the influence of the Hamiltonian f. And Hamiltonian evolution does not change Poisson bracket. And so we have a canonical transformation. Now, these canonical infinitesimal canonical transformations form a Lie algebra, and the Poisson, the commutator of two infinitesimal canonical transformation is another infinitesimal canonical transformation with the parameter given by the Poisson bracket between the two functions. We can also exponentiate these algebra and get the Lie group of finite canonical transformations. This would be this can be thought of as a result of a Hamiltonian evolution, where the Hamiltonian is f and the time is 1. So that's a group of canonical transformations. Now let's consider the notion of the dual space. The dual space would be also a space of all function f, small f now, and one can define one can introduce the parameterization so that the scalar product between small f and big F is just the integral of the products in phase space. So far, everything has been quite formal, but the last equations can be interpreted in a very nice physical way. If one think about capital F as a physical observable, and small f is the distribution function, then this formula gives us the expectation value of the quantity big F in the state given by the distribution function small f. One example, for example, it would be f equal p squared over 2m. That would be the quantity that capital F correspond to would be the kinetic energy. And the integral here would be the total kinetic energy of the system with the distribution function small f. The formula that we have here is semi-classical, analogous to the trace of F and capital F, where F here, one can think about this F as the density matrix. Now one can define the adjoint and co-adjoint group action on the Lie algebra and the dual space. And it turned out that in the way that we have introduced the dual space, the formulas for the adjoint and the co-adjoint group action are identical. Basically, these are exponentiation of the Poisson brackets. So acting a U on F, where U is the exponent of G, basically give us a rotation by just the Poisson bracket exponentiated in this way. And one can check that this preserves the scalar product. Okay, so how do we how all that is useful? Let's consider a reference state F0, which we are going to choose as the ground state of a fermionic system with rotational symmetry. So our reference state going to correspond to F equal to 1 inside a Fermi sphere, inside a Fermi surface with radius Pf and 0 outside. Now we know how to act on that reference state, any canonical transformations, and so we can define the co-adjoint orbit. That is a subspace of the dual space. Consists of all states which can be obtained from F0 by canonical transformations. These would be states which still have a sharp Fermi surface, because canonical transformation preserves the volume of the phase space. This would be a state with sharp Fermi surface with the same total number of particles. And so we now have a nice way to think about a Fermi liquid. A state of a Fermi liquid can be identified with a point on the co-adjoint orbit. And our task is to write down an action on trajectories that depends on the trajectories on the co-adjoint orbit. Okay, so this we have already talked about. Now let's work in perturbation theory. Expand F equal F0 plus delta F. And the group elements of the Lie group can be thought of as an exponents of some phi. And let's assume that phi is small for a moment. And expand the result of canonical transformation acting on F0 to first order in phi. So what do we find? That after acting on the initial state, we get another state where the distribution function is has a Fermi surface. So the Fermi surface is slightly deformed compared to the original Fermi surface, which I draw here, the round Fermi surface. Basically, the new state can be characterized by the height function, that is the radius of the Fermi surface along direction in momentum space, which is equal to Pf plus P cross gradient of x times phi, but this capital P is the direction in momentum. Now one has to talk about the ambiguity in this procedure. We say that the coadjoint orbit is a coset. That means that there is a set of there is a whole class of function phi, which correspond to the same point on the coadjoint orbit, that is to the same shape of the Fermi surface. And one can work out this ambiguity. It's easy to work out. I do that on this slide. Roughly speaking, sketching out, we have to figure out what are the elements of the small group H. That is group of all the canonical transformations that leave the Fermi surface invariant. And by using this ambiguity, one can fix the gauge. The gauge that one can fix the following gauge. That for function phi, instead of being a function of x, capital P, x and P is now a function of only x and the direction of P. Not it's invariant, it is the same function. This function does not depend on the absolute value of P. And so now we have, after this gauge fixing, that is choosing one single representative among all the functions that correspond to the same Fermi surface, we get a description of the state of a Fermi surface in terms of a function of x and theta. Theta, so in 2-dimension, theta is just a single angle that parameterize the point on the Fermi surface. Any questions so far? Okay, so now let me go to the.
Can I ask a question?
Yeah.
So I can certainly believe that for the Fermi surface, these shape deformations that don't change the topology will be gapless, right? As I make the amplitude small. But it's not clear to me that this is all of the gapless excitations. I might think that if I just take an electron, pull it outside of the Fermi C and put it just outside, this is a topology change. So you don't have this here, but that should still be gapless as I do this particle hole swap closer and closer to the surface. Is it secretly built in here, or am I missing those gapless states?
So all the gapless states that we are taking into account here are those that, roughly speaking, we take some part of a Fermi surface and then move it to somewhere.
Yeah.
Yeah. So as we see later on, this I believe this is enough at low end, at long wavelength, all the excitations of the particle hole types can be accounted this way.
Okay, by some superposition, basically. Okay, thanks.
Apparently, yeah. I will show some calculation that show that seems to be the case.
Okay.
Question?
Yeah.
I think this question may not be well defined and related with the previous one, but usually one of the main character of Landau Fermi theory is an emergent U1 momentum symmetry. So, which means, as you know, at momentum k, the number of nk is conserved. So at the Landau Fermi fixed point.
I believe this is this statement, strictly speaking, is not true. That is, that it's not correct. It's not a properties of the Landau Fermi liquid theory. So let me show you what I mean by that. So if I take this equation, for example, even if I turn off even if one turn off the electromagnetic field, we'll see that due to the presence of the Landau's parameter here, it's very difficult to be. It's not the number of fermions at a given momentum is not conserved. With Landau parameter, it doesn't. It simply is not conserved. So I believe there is a misconception in the literature.
So as far as the main point is that the effective Hamiltonian of at the Landau Fermi fixed point is written only in terms of density at the momentum k, nk, and nk prime, fkk prime. So that's the reasoning why Yeah.
Because the density does not commute with each other. So the reason is the following. One can actually try to write, as you mentioned, the Landau Hamiltonian as some kind of a function. Right? So there's a free part, epsilon 0 p ends of p of x, and some kind of a quadratic part, ends of p prime. And one can show that in order to get this equation, one have to have a non-trivial commutation relation between n and n. This is non-zero, and so the Hamiltonian no longer commute with the total number of particles at one given momentum.
I see.
In the presence of a magnetic field, that becomes even a sharper question. That is not the magnetic field breaks the conservation of electromagnetic field would breaks the conservation of number of fermion with a given momentum, even when there is no Landau parameter.
I see. Thank you.
Yeah. Okay, so now we would like to write down an action, and the action turned out to have a very nice form. So it has two parts. I'm giving you here just the result, and one can check that this action gives rise to the equation of motion that is exactly the Landau's kinetic equation. The two parts of the action is the following. There is a trivial, rather simple part. That is the Hamiltonian. Basically, that is that Hamiltonian that I've written before. That is the function of the distribution function. For free fermions, it just count energy of each of the fermion inside the Fermi surface and then sum them up. If there is a Landau parameter, we need a certain modification to that energy. But that's quite a well-defined function of the distribution function. What is non-trivial is the time derivative term, which has a form of a Wessel-Witten. It can be written in a certain Wessel-Witten form by introducing an extra coordinate, and the first term can be rewritten as an integral of a two form in time in this auxiliary coordinate. So in this way of writing, it is related to something in mathematics called the Kirillov-Kostant-Souriau symplectic two form. But in our case, this integral, one of the integral can be taken. You can write a simplified version of the action without the recourse to the extra coordinate, at the cost of having the Lagrangian density not completely invariant with respect to the class of equivalence of this U. Let's recall that U is way we use U here parameterizes a point on the Coadjoint orbit, and different U can correspond to the same point in the Coadjoint orbit. And so this integral, the Lagrangian density is not invariant under changing U without changing the point on the Coadjoint orbit, but it changes by a total time derivatives. Okay, so let me explain what is this Kirillov-Kostant-Souriau symplectic two form as mathematicians define it. So let's recall that we have a Coadjoint orbit, which has each of the point is on the Coadjoint orbit is a vector in dual space. So now the two form is mapped between two infinitesimal to tangent vector f1 delta f2 to a number, and that is defined in this way. This map is the scalar product between the state F, the point on the coadjoint orbit, and the commutator between two elements of the Lie algebra, F1 and F2, that generate this tangent vector. It turned out that one can show that it is this definition makes omega, first of all, independent of the choice of this element of the Lie algebra F1 and F2 that move the point F to the direction delta F1 and delta F2. That's one thing. And another thing is also non-trivial is that this omega is a closed two-form. And so that it can be used to write down the time derivative term in the action. And one can vary this action and check that the equation of motion that follows from it is exactly the Landau equation of motion. Okay, so these two terms in the action has physical, each has separate physical interpretation. The second term, of course, is the Hamiltonian, the Landau's parameter, etc. Enter the Hamiltonian. But the first terms can be thought of as a Berry phase acquired by a system, by the fermionic system, when the Fermi surface changes shape. So basically, these first terms tell us that if I have some kind of Fermi surface, and we change the shape of the Fermi surface as a function of time, and the Fermi surface can change its shape differently at different points in space, we'll trace out a trajectory on the coadjoint orbit, on the space called coadjoint orbit. And the first term tells us the Berry phase that is associated with this trajectory. So apparently, Landau's Fermi liquid theory has a very deep meaning that the Berry phase term is universal for Fermi liquids. It's independent of the interaction between particles. If we have a Fermi surface that changes its shape, the Berry phase it acquires is independent of the interaction between the original particle. The Hamiltonian may depend on the detail of the interaction that requires Landau's parameter, etc. To parameterize, the Berry phase term is universal. Okay, so yeah.
In this description, how can you introduce the role of curvature effect? Dispersion curvature, yeah, curvature. Dispersion, nonlinear. I mean, usually the previous, bosonization failed. One-dimensional generalization of bosonization fails due to they can't introduce the curvature effect well.
Okay, so the Hamiltonian for a free fermionic system is just basically integral over the pdx, epsilon of p, f of x and p. So it's written in this way. And in this way, it depends on the point f and can be rewritten in a slightly different way this way. So the nonlinearity in the dispersion relation is all in this function epsilon of p. So let me maybe show how it appeared a little bit later on in one calculation. I will show you where it would appear.
I see. One more question. So in this page, can you comment on? In the Berry phase term. So an immediate question is, how can I understand it? I mean, can I relate it with some anomaly if I gauge something background? So can you comment on that? Or...
I have
what kind of transformation? Yeah.
No, I cannot. I think there is this is a very interesting question, and one can argue that this, for example, this coefficient of this term has to be integer, for has to be quantized. The Weissman-Wheatstone term has to be quantized by considering certain global, like large gauge transformation. But I'm not prepared to answer your question about the anomaly. That's something I have to think.
Yeah, I see. Thank you. Yeah.
So let me show you what is the result of expanding this action to quadratic order over phi. So we have a prescription that's completely well defined. So we can apply it to any system. So for example, for free fermion. So here I'm just show you a bosonic description of free fermion to quadratic order over phi, this bosonic field. So here the result is rather intuitive. The action is an integral over phi of the action of a chiral boson, so one chiral boson at each value of theta, moving along the directions of theta. N of theta is the unit vector along the theta directions. So one boson per each theta. The density operator is the sum of the density of each of the chiral boson, and we can compute, for example, the 2-point correlation function of rho and reproduce what one would get from the one loop fermionic one loop graph. Now one can go to a nonlinear order. Now in this case, the calculations start to become a little bit more complicated because we have to expand these terms to higher order in phi, but the procedure is completely well defined. That is, we just need to compute the Poisson brackets and that's it. So in this case, again, I'm writing down the theory of free fermions. Free fermions turn out to map into a interacting theory of these bosons. The interaction between bosons, first of all, they come from things like epsilon double prime. So this epsilon is a function of P, and you can see this epsilon double prime here is the curvature of the dispersion relation. So that term would be responsible for interaction between boson even in 1+1 dimension when the epsilon is not linear. Now, but there are more interesting terms in the Lagrangian. Basically, we have derivative with respect to theta. So this derivative with respect to theta here in the action means that bosons at different theta are coupled to each other in this description. Not in the Hamiltonian. In the Hamiltonian, there is no coupling between different theta, but in the Wess-Luminovic term with different theta, boson with neighboring theta talk to each other. So one can use this cubic level action to compute 3-point function of density. So the 3-point function rho, rho, rho. In the fermionic theory, actually there are two diagrams that contribute to this green function. The two diagrams simply differ from each other by the direction of the momentum of the fermions. In the bosonic description, we have just a set of three graphs. One has because we have a 5 cube vertex in our bosonic theory. Another diagram comes from the fact that in our value and our expression for the density, there is a phi square. Summing up these two diagrams on the right, we can check that we get the result of summing the two diagrams on the left. It's a very non-trivial check, which we are not able to do completely, but we have done many checks in different regimes at random points, and we find complete agreement. One interesting fact is that the two diagrams on the left in the fermionic theory almost cancel each other in the regime when the momentum of the external legs are small. So if the momentum here, omega of order q, which is much smaller than pf, we find that each of these individual dual diagram is 1 over q, but the sum is q to the 0. There is a cancellation of the leading 1 over q behavior. In the bosonic picture, this cancellation doesn't happen. Each of the diagram already automatically of order q to the 0. So in some sense, the bosonic, in this regime, in this sense, the bosonic theory is more natural, more give rise to a more natural counting of the importance of the interaction. Okay, Landau. Yeah.
One more question. Is this your bosonization scheme connected to one-dimensional bosonization scheme? Can I interpret some connection between your, if I apply your to one dimension? Can I?
Yeah, we can find the following, that if the dispersion relation is linear, then all these series truncate, and we get the exact chiral boson. Chiral boson is the exact dual of fermion with linear dispersion relation. With non-linear dispersion relation, we start to get interaction between this boson. So we can.
I see. So my question is, so usually, usual bosonization procedure, you know better, some flux attachment, some changing statistics, in this, there is some fermion boson mapping but here you just use the density, some dual of density fluctuations. Sorry, just the density fluctuation variable directly. So in that respect, but you mentioned your result is the same when in the linear dispersion limit in 1D. But
there is in this approach we don't know. Maybe there is, but we don't know the relationship between the fermionic operator and the bosonic operator. Like psi equal e to the I pi. We would not be able to guess. We will not. It's not part of this construction.
yeah, I see. Okay, thank you.
And I know what we know is that this phi is actually a compact variable in any dimension from some argument based on large gauge transformation. But that's all that we know.
I see. Thank you.
Okay, so let's talk a little bit about extension of this formalism.
One more. How to introduce electromagnetic field coupling? Electromagnetic field coupling, yeah.
We can couple the theory to any to a large class of basically we can gauge the canonical transformation. Whole group of canonical transformation can be gauged. So the U1 particle number is just a subgroup of that group of canonical transformations. So we can do that.
So can you give me some example electromagnetic field coupling for this?
I think what would happen is the following. I'm probably can do it with some approximation here, but this dt have to be transformed into dt minus a0, and then in this p here has to be changed by p minus a, and that in the case of free fermion, that's all that we need to do to couple the theory to external electromagnetic field. There's only two terms, not two modifications one need to make.
Thank you.
And then there's a gauge action for A. Okay, so now toward extension. So one thing that one can notice is the following, that the group of canonical transformation can be thought of as long wavelength limit of a group of, that is, of the algebra of canonical transformation is a long wavelength limit of the algebra of fermion bilinear. Fermion bilinears Seidegger form a closed algebra, and in some limit this algebra reduces to the algebra of canonical transformations. And that suggests a way to include spin in the theory. One need to include also operator of the form Seidegger sigma A psi. And that would take care of the spin degree of freedom. We enlarge the group of canonical transformation to a group that generated by Seidegger psi and Seidegger sigma A psi. The BCS theory can also be treated in a similar way. We extend the algebra of canonical transformation to include operator, the BCS operator, bilinear, but in the BCS channel, psi x, psi y, Seidegger x, Seidegger y. So we can then again apply the formalism of coadjoint orbit, but with a larger algebra in a larger group, larger than the group of canonical transformations. Okay, so let me conclude. The method of coadjoint orbit provides a natural way to write down an effective theory of a Fermi liquid. The result of this method is a nonlinear bosonization procedure. That is very well defined. One doesn't need to, one just need to follow the mathematics, and one can generate all the coupling constant between the boson. So one thing that we see here is that generically the boson at different point in theta on the Fermi surface start to couple to each other. We can check that it reproduced the linear and nonlinear Fermi liquid response. We explicitly check that for 2-point function, 3-point function, and we can also show that the equation of motion that comes out from the action coincides with the Landau's equation of motion, kinetic equation. Perhaps this may be a suitable starting point for the study of non-Fermi liquids. So that is something that we are currently trying to think about, whether this formalism could be useful. At least provide another, at least we have seen that it provides another way to see, to understand the non-Fermi liquid, the emergence of non-Fermi liquids from a Fermi liquid when we couple it to a gauge field or a boson, or a critical boson. Well, thank you very much for your attention.
Thank you very much. Now the talk is open for questions. Please feel free to ask. Yeah.
I have a question. This seems like your construction is now explicitly at finite density, but if I understand correctly, you would no longer have a sign prop if I tried to do Monte Carlo with your action, right? Could you do this and then really have some sort of Monte Carlo approximations of the partition function at finite density this way?
I would guess there's still it's, first of all, it's a kinetic, it's effective field theory, so we have to put some cutoff on that.
That's fine, yeah.
Because
but can you take the WZW term? I guess that's the question.
Yes. So in the real time, this term is imaginary.
Okay.
Yeah, but now you ask, what can we go to Euclidean space?
Yeah.
Still there is. I have to think, but I'm not 100% sure what would be the sign of that. Would there still be a sign problem with that?
Yeah.
Term?
Exactly.
Yeah.
The other thing I wanted to ask is, so implicitly in your dispersion relation epsilon, this is where the Landau parameters are?
I think it's not yet. the Landau parameter would appear, for example, if we write down a term that is quadratic over dispersion over delta F, it will be non-local in momentum space. So the term that come from dispersion relation epsilon here will come from just a single particle dispersion relation, so local in P. So, but in principle, one can also include the Landau parameter, which is local in space but non-local in momentum space.
Yeah, more questions? Then let me. So I want to introduce momentum space Berry curvature here. So in your term, Berry Fermi liquid. So how can also related? How can I extend the canonical transformation in the presence of some Fermion bilinear operator? So can you elaborate more this two part?
So your question is how to
introduce a momentum space Berry curvature into this canon. So I want to extend this into
So this one,
correlation functions, density in the presence of Berry curvature, and
that can be presumably has not been done, but I think it can be done by modifying the notion of the phase space in the Poisson brackets. The momentum space, Berry curvature can be thought of as the non-commutativity of space. So X and X becomes some Berry curvature that depends on P. So that will allows us to, that if we include this into the definition of the phase space and the symplectic form in the phase space, can define the canonical transformation at the S-low transformation that preserve the new canonical, the new Poisson bracket, and presumably that will be the theory of fermions with, say, a Dirac point in momentum space in 3 dimensions, for example. And so this is
how about fermion bilinears? How can I extend the canonical transformation to include the superconductivity? So simply, I don't understand how to extend the canonical transformation with the introduction of fermion bilinears.
So here this fermion bilinear has certain commutation relation that it's like that. Let me try to write. So these operators, these O of X and Y, they form a closed algebra. And now one can do a Wigner transformation, that is transform with respect to the relative coordinates, and rewrite this operator in terms of the center of mass coordinates in P. And when one write the commutation relation between this O of X and P, we find something that is very similar to a Poisson bracket structure. And so these operators can be thought of as the generators of the group of canonical transformation. It's something that can be defined in quantum theory, but in the classical limit, semi-classical limit, it becomes canonical transformation. And now we have to introduce new fields like O2 of X in P and O minus 2 of X in P. And they would have non-trivial commutation relation with O. So we wrote that in our paper, right?
I see.
Exactly, but like O2 and O minus 2, the commutator would be that O, for example. There's one of these. So we have a new group, a new algebra, a new group. and we need to just apply the formalism to this new group.
I see. Okay. Thank you. So more questions? So my last question is, so although you just slightly mentioned about non-formulated effective long-range interaction treatment, can you elaborate more? How can you, so in which direction? Some idea?
Oh, we just try to understand whether the non-Fermi liquid, so we have an action which we can do power counting with. All right, it's a field theory, so we can classify the operator as relevant, irrelevant operators. We can see that, for example, in 3 dimensions, if we in 3+1 dimension, coupling of the if we couple electromagnetic fields to the Fermi surface, we have a marginal interactions. In 2+1, that would be relevant interaction. So these basic things, we reproduce just the basic things that already known in the literature about what kind of long-range interaction induces, changes the Fermi liquid behavior. But we were not, we haven't go further than that. In principle, we should write down, for example, renormalization group equations. We might try to do some epsilon expansion and get the Fermi liquid, non-Fermi liquid fixed points. That's something that we are going to on. But the procedure here is quite similar to what one would do in quantum field theory. That is, write down try to analyze these interaction terms, and then find out what kind of scaling.
I'm somewhat confused. So you didn't introduce effective long-range interaction directly. Am I correct?
We can couple the theory to electromagnetic field, for example. Let's assume that.
I see. Okay.
Yeah.
I see.
Yeah.
But presumably you can also include just a density Coulomb interaction as well.
Density.
I mean, you can write this down. Yeah, rho of x, rho of y over x minus y.
Yeah,
can you add this to the Hamiltonian?
That would have be by screening, so wouldn't give any non-trivial long range. It will not remain long range because there is a fermion loop that addresses.
I see.
Propagator.
So, more questions? Further questions?
Yeah, may I ask one question? I mean, so when people talk about non-Fermi liquid coming out of this coupling to soft form, I mean, they usually talk about the situation when it's coupled to Gapless bosons. So I'm just wondering, like, is there any type of Gapless bosonic excitation that would be easier to treat in your formalism?
I think this there are probably the bosons and the gauge field would be equally hard in this formalism. What can make it easier is changing the exponent in the propagator of the bosons from 1 over q squared. We can try to do 1 over q to the power of 1 plus epsilon. That make the calculation easier.
But usually such kinds of non-local regularization scheme may miss some quantum corrections,
It might be, it might be subtle to analyze.
So basically you're saying having a local coupling between, I mean, this electrons and boson is not an advantage in this formalism?
Well, it's an advantage because we can deal with the local field theory, count the dimensions of operator. So it has an advantage.
Okay, thank you very much.
Oh, yeah, further questions? If not, let's thank Professor Jameson very much. Yeah.
Thank you.
Let's